committee interact with anyone. So if you're ready, we'll go ahead and get started.
Okay, great. Like Dr. Nelson said, my name is Emily Escamilla, and I will be presenting on assessing the prevalence and archival rate of URIs to Git hosting platforms in scholarly publications. So before we can jump into the actual meat of my thesis, we need to establish two facts. The first is that the web isn't permanent, and the second is that scholars are including URIs to software products in publications. So if you've been using the web for any length of time, you've probably come up on a screen that looks like this. We see 404, the web page that you are looking for is not found. This is just one of many examples where we see that the web isn't permanent. The page that you are looking at now might not be available tomorrow. And this has been widely studied by scholars, including Klein et al. They looked at 3 different corpora from scholarly publications, and they looked at the prevalence of URIs within those scholarly publications. And as you can see in gray in this figure, the number of URIs within the publications has grown dramatically. And on the bottom, you can see in yellow, the number of URIs that have reference rot. Reference rot is the official term for what we've all experienced on the previous slide, where the page you are looking for cannot be accessed from that URI. And as you can see also in the yellow line going across the figure, as you go back, older articles experience a greater level of this reference rot. And Klein found overall 1 in 5 articles suffers from reference rot. So we established that the web isn't permanent. So now we'll look at our second fact. Scholars are including URIs to software in their publications. And so here's an example from the archive corpus. We have an author here saying that we have begun work on an open source software package named Odin that aims to implement this computational framework in an efficient and accessible manner. And there they give the GitHub URI where they can say, for the exact implementation of how we did this, go to this URI. Here's another example from the PubMed Central corpus. The authors here are saying that the translation of the transcriptome assemblies was conducted using a series of custom Perl scripts. So instead of listing out the exact implementation in their methodology, they're just pointing to this GitHub URI to say that is where our methodology lives. So these software products are functioning as an extension of the methodology. What happens when these two facts collide, that the web isn't permanent and that scholars are including URIs to software in their publications? You get something that looks like this. This is the excerpt from our archive publication that I mentioned earlier. And this is what happens when I go to the GitHub URI that they provide. That URI that they're saying, again, here is where my methodology and the implementation of that lives. It's no longer available on the live web. Why does it matter that the code is missing? And so to answer that, we have to introduce reproducibility. Reproducibility is a cornerstone of scientific research. The ability to verify results and build on those results are key aspects to a thriving scientific community. Sir Isaac Newton is credited with saying, if I have seen farther, it is by standing on the shoulders of giants. So the research that we are doing today is built on what other people have done in the past, and the research that people will do in the future is built on what we are doing now. And all of that is contingent on access to the original data and methodology. And as we just saw, software is a key part of understanding that methodology. So briefly, I want to mention the difference between these three that you've probably heard interchangeably of repeatability, reproducibility, and replicability. On the bottom, repeatability is the same researcher with the same data and the same method should get the same results. Reproducibility, what we just discussed, is a new researcher with the same data and the same method. And then you have replicability, which takes it one step farther, where you have new researcher, new data, and a similar methodology. And this work is going to support both reproducibility and replicability. So we've identified the problem that code is not immune to the reference rot that we know exists. Now we need to understand the scope of the problem. And in order to do that, let's introduce the major players. So first, we have Git and GitHub. Git, as you can see on the left, is software that's installed locally on your local computer, and you access it via the command line. It's a tool for managing different versions of files within a repository. The repository is just the collection of files. GitHub is a service that's hosted on the live web. As a result, it has a graphic interface that you can interact with, and that is just a hosting platform for these Git repositories. As you can see in orange, Git allows for making commits, pushing changes, pulling changes, and managing branches within that repository. GitHub supports all of those features and then some. So as we can see, they have a user interface like we already mentioned. They also enable collaboration with pull requests, forked copies, merging repositories back together, as well as issue management. So here's an example of a GitHub issue page. As you can see, the owners of this repository are doing a poll. If you use this, please answer if you use this repository, please answer this question. They're asking for feedback from the people that are using their repository. As well as on the bottom, you can see 3 different issues where users who are reporting errors that they found, suggesting changes and things like that. Issues pages are just one of the places within GitHub that we see users of a repository and the owners of the repository collaborating to determine the future direction of the code. All of this adds context to the code itself that lives in GitHub. So Git hosting platforms are really commonly used. On the right, we have a bunch of logos for different Git hosting platforms or GHPs. They're great for version control and make code discoverable. But as we've already mentioned, there's increasing number of links to GHPs within scholarly publications, but they're not permanent. If you've never seen these logos on the bottom, they're for Google Code and Gitorious, and they no longer exist. So if you haven't heard of them, that's why. Even despite users depositing their code, expecting some kind of permanency, those services are no longer available. I'd also like to mention that the GHPs that are in green is what we will be collectively referring to as GHPs. So we looked at GitLab, GitHub, SourceForge, and Bitbucket for the remainder of this study. When it comes to scholarly products, the publications themselves are well preserved. Initiatives like Locks, Clocks, and Portico archive scholarly publications, but when those publications reference web at large resources or source code, those are not preserved. So now we'll introduce 3 different digital libraries that contain archives of these GHP repositories. So first we have the Internet Archive with the Wayback Machine, Software Heritage, and Zenodo. So the Internet Archive preserves the web at large. They capture the entire web page, and their goal is to be able to capture it in a way that users are able to look back and see what that web page would have looked like at the day and time that it was captured. They provide a unique URL for each capture that includes the day, time, as well as the original URL of that capture. Second is Software Heritage. Unlike the Internet Archive, they are solely focused on preserving software products. They maintain the commit history that we find within Git, and they create unique PIDs, permanent IDs for software objects that they are hosting. And then lastly, Zenodo supports open access to digital resources, and they are really popular in the scholarly community because they mint a DOI, or a document object identifier, for each of their digital resources. And their versioning matches the GitHub releases that you would see within the repository. So to understand the differences between these 3 digital libraries, we're going to use TensorFlow repository as a case study. So this is what it looks like on the live web. If you looked at it today, it would probably look something like this. And if you looked at it in the Internet Archive, it looks like this. Notice that it virtually is identical. Again, Internet Archive is preserving the exact look and feel of that web page at the time that it was captured. So this is what we call a memento, or an archived version of a web page. And you can see in the top right corner that this was archived on June 28, 2023. So in theory, this is what this page looked like on that date. In Internet Archive, with how they capture the page, they're capturing everything in this blue circle, all of the extra stuff that adds context to the repository itself. And because of that, we can use the Internet Archive's Mentos to compare and see UI changes over time. So on the left, we have an example from November 2015 of what this repository looked like, and then now in 2023. So you can see even in the metrics that those have slightly changed. From on the left, you have watch, star, and fork, and now on the right, it's notifications, fork, and star, as well as the main menu used to be on the right-hand side, and it's now along the top with additional features. Again, because the Internet Archive is preserving the entire web page, we can see changes like this within the mementos. When we look at software heritage capture of TensorFlow, this looks nothing like what we just saw in the last 3 slides, because software heritage is only capturing the Git portion of the software. They're only capturing the software and not everything else around it that is supported by GitHub. So they still have the commits, they have the branches, all of the version history, but they're missing, again, the issue page and things like that that add the context to the repository. And when we look at Zenodo, this will actually be the last time we mention it, because they do not support searching for a URL. When I try to search for the TensorFlow repository, you get an error that says the syntax of the search query is invalid. Because they do not support searching for URLs either on their UI or in their API, we excluded them from the study just due to scale and scope of the study. So with that, we addressed 4 research questions. First, how often do authors include GHP URIs in scholarly articles? 2, what is the prevalence of these GHP URIs on the live web, in software heritage, and in web archives? 3, outside of these GHPs, what hosting platforms are scholars including in their publications? And lastly, does popularity affect the likelihood of a GitHub repository being archived? So let's jump into the first one. But with that, we need to understand our corpora. We looked at Archive, which is a STEM preprint service, and we understood it as a representative sample of STEM publications. They do have a bias towards physics as well as computer science within their corpus. They have over 2 million submissions that are publicly available and programmatically accessible that made them useful for our study. And we used a corpus of publications from April 2007 to December 2021. Archive allows authors to submit multiple versions of the same submission. And so we used the latest version and understood that version to be most representative of what the authors intended. Our second corpora was the PubMed Central, or PMC corpora. It was a full text journal archive with biomedical and life science journals. They have over 7 million articles. Again, they're publicly available and programmatically accessible. And just to maintain consistency with the archive corpus, we analyzed publications from April 2007 to December 2021. So in total, our corpus contained 2.66 million publications. And from those publications, we found over 7.8 million URIs to the web at large. And of those, we found over 235,000 URIs to one of the 4 GHPs listed here. And as you can see, GitHub is by far the most popular of the 4 GHPs, with over 92% of all GHP URIs being to GitHub, followed by SourceForge, and then Bitbucket, and then GitLab. We looked at the use of URIs over time. Starting in 2007, there's about 1 URI per publication. Now in 2021, there's an average of 5 URIs per publication. And we see this across both of our corpuses. You can also see in the green line at the bottom, a slight increase as well in the use of GHP URIs in that archive corpus. So if we zoom in specifically at the archive corpus, this is the use of GHP URIs within the archive corpus. And you can see it's pretty low, pretty rare to see a GHP URI until about 2014, when GitHub really starts building in prevalence. And by 2021, 1 in 5 archive publications contains a link to at least 1 GHP. When we look at the PMC corpus, we see a similar story. SourceForge started out strong in 2007, 2008, and then dropped off. In 2015, we see that GitHub overtook SourceForge as the most popular GHP in this PMC corpus and has steadily increased to 2021. I'd like to note that the scale of this is significantly different than the previous one. For GitHub, for example, in 2021, there's an average of 2.5 of publications that contain a GHP URI, which is different than, or significantly different than what we saw with 20% in the archive corpus. This might be due to the computational science and physics leaning of the archive corpus compared to PMC being biomedical and life science. So we see difference in the disciplines in the scale here, but we are seeing similar trends across both corpuses. So then we looked at if a publication contains a single link to a GHP, how many links do they have? So here we see that 32% or a third of all of the publications contained more than one GHP URI, which accounts for about 70,000 publications. And as we continue to follow this line, we see that 14% contained more than 2 GitHub URIs. As we follow even further, we see that 0.6% of our corpus contains more than 10 GitHub URIs. And a small percentage of a large number is still a large number. So that represents 1,325 publications that are containing over 10 GitHub URIs. And when you think about how scholars and authors include references and include URIs in their publications, they're only including them if it matters to their research. Whether that's something that they're building on or something that they're referencing or something that they created, they're placing a heavy emphasis on the holdings of GitHub to support their study. And we cut off this line at this figure at 150, but it actually could have gone all the way to 896. There's a publication that contained 896 GitHub URIs. So this publication is titled A Comprehensive Feature Comparison Study of Open Source Container Orchestration Frameworks. So they were looking at a whole bunch of frameworks, and then here on the right, you see a table that shows just how they got to that many. So each of the check marks is showing that that framework has that feature, and then they would include the URI to the documentation, which largely live in GitHub, to say like proof of this is over there. So this publication in specific is showing us that authors are not just including URIs to their own software products, but also what would happen if all 896 of these links disappeared and were no longer available. That would really negatively impact this study and our understanding of this study. So now on to our second research question. What is the prevalence of these GHP URIs in the live web, in software heritage, and in the web archives? We used Memgator, which is a memento aggregator, to query 12 different web archives. So you provide Memgator with a URI and it queries these 12 and returns back any mementos that it has. So as you can see in this table, Internet Archive provided almost 59% of all mementos, and Bibliotheca Alexandria Web Archive provided 23%. But it's worth noting that in 2022, Bibliotheca Alexandria Web Archive became a mirror of the Internet Archive. So when we look at those two together, they returned nearly 82% of all of our mementos for these GHP URIs. For software heritage, we had to change some of our URIs a little bit for the Software Heritage API because they do not support deep link searches. So when I'm searching for this github.com and it's all the way down the file path for this specific file, I get an error that says no origins match the search criteria were found. So we had to transform these deep link URIs to this github.com/user/repo format. And so as a result of that, it would be github.com/tensorflow/tensorflow. And so these short URIs are then what we used for the Software Heritage API. Because when we then search for the shortened version, the repository level URI, it does show that they have it. So you just had to shorten it, and then the API was able to find that result. So when we looked at these URIs on the live web, we found that 93.98% of these URIs were active, or active also means publicly available, because in this context, GitHub repositories can be private, but then you can't access them. Like someone might be able to access them, the owner might be able to, but they're not publicly available, which then does not support reproducibility as we discussed. So, and again, similarly, as we said before, a small percentage of a large number is still a large number. So even though it's only 6% that are not available on the live web, that still represents 8,882 rotten URIs. And that impacts a lot of different publications that are including these URIs. GitHub had the highest number of active URIs with close to 95%. Bitbucket had the lowest with 75.86%. For software heritage, we found that only 66%, or about 2/3 of our repository URIs were in software heritage. And then GitLab had the highest percentage with 85%, and then Bitbucket and SourceForge had by far the lowest with nearly 17%, and then 24% were in software heritage. It looks a little bit more promising for the holdings of web archives. Overall, we had about 81% of the GHP URIs were found in the web archives. GitHub still had the highest percentage with 82.25%, and GitLab here is the lowest with only 64% of the GHP URIs being archived in the web archives. So next we looked at essentially how did the holdings of software heritage and the holdings of the web archives interact essentially, or overlap. So in the green, you can see the percentage of GHP URIs that were found in both software heritage and the web archives. In blue, you can see the percentage that's only in software heritage. In orange, only in the web archives. And then in red, we have the percentage of URIs that are not in either software heritage or the web archives. So we found that overall, 54.4% of the URIs were found in both software heritage and the web archives. It's also worth noting that very few of the software heritage holdings were unique, meaning that for the most part, the large majority of software heritage URIs were already captured by the Internet Archive. But the same is not true in the opposite way. We see a large percentage of URIs that are only available in the web archives and not captured by software heritage. And then also we found that 13.3% of our GHP URIs are vulnerable. Vulnerable meaning that they are not archived anywhere else, and that if they were no longer available on the live web, they would disappear. To put that in context, for GitHub's 12.9% that are vulnerable, that represents over 15,000 GitHub repository URIs. It's a lot of publications that would be impacted if those URIs were no longer available. Next, we looked at rotten GHP URIs. So of the URIs that are no longer available on the live web, have they been archived? And so you can see in red, you see the percentage of URIs that are unrecoverable, meaning that it's no longer available on the live web and there is no archived version of it in software heritage or in the web archives. And we found that about 1/3 of our rotten URIs are unrecoverable. And that is higher for GitLab with 38%, and then Bitbucket and SourceForge had 19.4% and 18% unrecoverable rotten URIs. So for our third research question, outside of these GHPs, what hosting platforms did scholars include in their publications? To answer this question, we worked with Dr. Wu as well as his PhD student, Lamia Salsabil. They created a machine learning classifier that identified open access data and software, or OADS, URIs. Their classifier uses a combination of regular expressions as well as machine learning to determine if a URI, and they looked at that URI in the context of the sentence, to use that to determine if it was an OADS URI or a non-OADS URI. And so on the left, we see two examples of OADS URIs, as well as the sentences that they were in. So from regular expressions and what we did in our previous study, we see that GitHub is an OADS URI. Like if you understand GitHub, you know that that's true. But that might be less apparent when we look at the second example, IBM.biz. That would have probably taken a couple clicks to investigate what is that data, is that software. So using a classifier, it automates that process instead of having to manually figure that out. So we see that that's an OADS URI, and on the right, we see an example of a non-OADS URI. Again, might not know off the top of your head what galaxyzoo.com holds, but by using a classifier, we're able to automatically classify that that is not an OADS URI. So we ran that classifier on our archive corpus, and we see in red the total number of URIs, in blue non-OADS URIs, and in orange OADS URIs. And all three categories have grown and actually tripled over time. So for example, the number of total URIs in 2007 is about 0.4 to now in 2021, we have about 1.2 URIs per publication. So with that, we wanted to look at the percentage of these URIs in the classification. So for example, in the blue line, you see that non-OADS URIs has actually decreased over time. So it started above 70% of URIs were non-OADS URIs, and now it's under 70% are non-OADS URIs. With that, we've seen an increase in the green line. You can see GHP URIs. And again, just like we've seen in the previous two research questions, starting in 2014, that number has increased of the prevalence of GHP URIs within the corpus to now going from just about 0% in 2007 all the way up to about 15% in 2021. And with that, the percentage of non-GHP OADS URIs has decreased since about 2016. So being very similar to the percentage of GHP URIs here. So we looked at the total count of GHP URIs and non-GHP OADS URIs. And you can see, again, the same slope and the same pattern that we were seeing with our previous studies for the GHP URIs here in green starting in 2014, increasing dramatically. But starting 2007, there's about 500 URI difference between non-GHP OADS URIs and GHP URIs. And that has grown steadily over time. But in 2020 and 2021, we see that for every GHP URI, there is a non-GHP OADS URI. So this points to a need to be able to identify those non-GHP OADS URIs. We can't just look for GitHub, GitLab, SourceForge, and Bitbucket. We'd be missing about half of the OADS URIs that are being included in these publications. And especially as we go to older publications, you really need to be able to identify those non-GHP OADS URIs in order to capture the software and the data that these scholars are including in their publications. So then we saw that there obviously were a lot of non-GHP OADS URIs, but where are they coming from? Are they all coming from the same place? So that's what we looked at here. We found that there were about 50,000 unique host names for these non-GHP OADS URIs, and that host name is just boiling down the long URI into essentially a shortened version, or the host name. So we see a list of those host names in the table on the right. So like DOI.org or W3.org is the host name. And these are the top 15 most prevalent host names that we found. But as you can see on the bar on the far right, there were 49,000 of our 50,000 host names were only used between 0 and 50 times. So there are a lot of host names that are only used a few times. But then as we follow that tail out, like you can see this bar here is representing cds.cern. So there are some of these host names that are used more popularly than others. But we've seen now that there are a lot of different host names. There are a lot of these non-GHP OADS URIs, and using a classifier essentially fixes that, or helps us to address that problem, because these classifiers allow us to detect URIs of these lesser known platforms. So here's an example of that. We have, this is from Thomas Jefferson Lab. If you're from around here, you've probably heard of it. It's a Department of Energy lab. But if you're not from here, you maybe haven't heard of it. So if we had to write down a list of all of the data and software URIs, if you're from here, you might include this. And if you're not from here, you might not include it. This URI in specific is for CODA, which is a data acquisition system specifically for nuclear physicists collecting data. So that's a really niche population who probably thinks this is really important. So here we're seeing that popularity doesn't necessarily match with importance. And so even though this might not have been included very many times, it's worth capturing and worth preserving. And a classifier allows us to capture things like this that might be more niche and you might not be able to capture if you just had to manually write down a list of all of the URIs to look for. So with our last research question, does popularity affect the likelihood of a GitHub repository being archived? So we looked specifically at GitHub for this, and we used their engagement metrics of forks, stars, and here it says watches, but we're going to refer to that as subscribers. So we're using these engagement metrics to determine popularity, and we use the GitHub API to get these engagement metrics for each of the GHP URIs that we identified in previous research questions. So we used a Mann-Whitney U-test to compare these two populations. And essentially, the Mann-Whitney U-test says that the probability of an item from one population being greater than the value from another population is equal than for like swapped. So for example, the number of forks for a repository that's not been archived being greater than the number of forks for a repository that has been archived is equal to the probability of the inverse. And so Mann-Whitney U-test allows you to then reject that null hypothesis and to identify whether those populations are statistically significantly different. So here we looked at fork subscribers and stargazers for each of the three archives. So for example, we're seeing that there's 100%, nearly 100% confidence level, as you can see by the p-value here of 0, means that it was so infinitesimally small that the computer just returned 0. So nearly 100% confidence in rejecting the null hypothesis. So there is a statistically significant difference between the engagement metrics for repositories that have been archived by Software Heritage and the Web Archives and those that have not been. And we see, and then we identified that there's a difference, and we used the Cliffs delta to measure the effect, or essentially how big of a difference is there. So we see that there's a small effect size for all of the categories except for forks and Software Heritage, and then stargazers in Software Heritage. And then let's look at this visually. So here's an example of looking at the number of forks. And in blue, the blue bars represent repositories that are not in Software Heritage, and the orange is repositories that are in Software Heritage. So as you can see with the blue bars, they're more left justified and have a shorter tail than we see with the repositories that are in Software Heritage in orange. They a little bit more right justified and then have a much longer tail, showing that there here we can clearly see that there is a statistically significant difference between the two populations. Here we can see a small effect size. So as you can see, it's much less clear or able to like visually see the trend, but you can still identify it. That on the left, left justified is the repositories that are not in the Web Archives in blue. And then again, that the repositories that are in Web Archives are in orange. So for future works, you could use the extracted URIs that we found through our research questions to test GHP archiving approaches at scale. So there are some approaches like Tracer or Web Recorder that are working to archive essentially special or niche web pages like GitHub. GHPs have different needs for being archived. For example, if you're missing the zip file, like that might matter more, and that might be different than for a typical web page. So tools like this are looking to essentially answer that problem. So we could use this data set that we've created to test those archiving approaches. A second is investigating other corpora or disciplines. Like I mentioned, ours are biased towards computer science as well as physics, and then the PMC corpus was biomedical and life science journals. Potentially these trends would be different if we looked at other corpora or disciplines. Third, measuring memento quality for these existing mementos. We just looked at whether there was a memento. We didn't look at whether it was a good memento or whether it would be actually beneficial for reproducibility. And then lastly, we could implement these extraction methods in a workflow for curators and archivists. Like if they were to submit a publication, move through this workflow, and it would end up archiving the software URIs that are present within that publication. So in conclusion, we addressed 4 research questions. How often do authors include GHP URIs in scholarly articles? What is the prevalence of these GHP URIs on the live web, in software heritage, and in web archives? Outside of GHPs, what hosting platforms are scholars including in their publications? And lastly, does popularity affect the likelihood of a GitHub repository being archived? And 3 of these are either already published or were submitted for publication. Our key takeaways, we found that scholars are including GHP URIs in publications. Specifically in 2021, 1 in 5 archive articles contained a GHP URI. We found that most GHP URIs are live, but 13.3% are vulnerable. We identified that a classifier allows us to identify the vast number of OADS URIs, and also that there is a relationship between repository popularity as well as archival rate. And there's also the GitHub URI that contains the data sets, our extraction methods, and our statistical analysis as well. So with that, I'd like to open up to any questions.
Great, thank you. Questions for Emily? Don't be bashful. Who wants to go first? Prove to her that you were paying attention. Dr. Weigel, are there questions online?
Not yet. I was just going to let everybody know to type it in the chat or
Okay, yeah,
type
so
up.
we can't see the chat from here, so we'll count on you to monitor that, please.
So, you mentioned about Zenodo. So you said like we can't search from URLs, but does it have like keyword search? Can you tell a little bit about it?
Yeah, so there are, I wonder if I should know
So,
this answer, but I might.
Repeat or paraphrase the question for the recording.
Yes, okay. I don't have that slide. So Himarsha asked a little bit more about Zenodo. How do they support searches? If you can't use URLs, is there another way? So the answer is yes. They do support keyword searches. So like, for example, with the TensorFlow, you can search TensorFlow, but it was the official GitHub repository was the 7th hit, and you had to filter out like, I only want software. And then you have to really dig in and try and determine like, is this the official GitHub repository? So yeah, it takes a little bit more manual effort than just being able to, like, if you have the URI already, it's not rapid to be able to identify the Zenodo copy of it, but they did have it. It was just the 7th hit.
Okay.
Yeah.
So it's like, I think it was on 58. It was the one about the like a completely non-existent.
Yeah. That?
Great.
Okay.
So on this one, so GitHub, has the like highest one, and I'm kind of surprised that GitLab has the highest, considering like the volume that is on GitHub compared to like the other platforms.
Yeah.
Was there like a specific reason maybe they popped up for why GitLab had a higher percentage than the others? And then also kind of just tailing on that, like was there was there like a specific kind of or an overwhelming kind of reason for a lot of it? Like maybe that your organization changed the name, or maybe someone deleted the repository or changed the name of the repository? Was there like a specific kind of overall reason why so many were missing for the different platforms? Or like could you categorize kind of what the reasons were that led to them?
Yeah, so I'll paraphrase for those online. So the first was why does GitLab have the highest percentage of rotten and unrecoverable URIs? And then for that one, we didn't really look into why or like what would have caused that. And then the second question was, just like in general, why?
Could you like kind of categorize?
Why did these?
Were you able to categorize the reasons why they were getting leaked from, like organizational change or repository name changes, deletion?
Yeah, so the second question was about like, did we look into why these were rotten? No, we didn't specifically look into why they were rotten. GitHub does still support like redirection. So like, for example, if you, I think it's like M Bosak or something like that, but that redirects to D3. Like he was the original guy who made D3 repository, and it automatically links to like redirects you to a D3/D3. So there is some of that. So these are they're either private or something like that. Yeah, so we didn't look into those specifically, but we do know that a lot of these do support the redirecting. So they're either taken off, made private. Yeah. Yes.
We have an online question. Can I ask that one?
Yeah.
Okay, so Jimmy is asking, is there any work on analyzing pull requests and their integration with respect to archiving the repos?
Like we didn't look into that specifically. That's definitely part of being able to archive the entire repository and the GitHub experience as essentially. I think what you're getting at is that the pull requests have a direct relationship to how the repository then looks after the pull request. And so that's essentially what we're getting at, is being able to track those pull requests helps us to better understand what happens within the code itself. So you're able to, so like if the pull request said closed with this commit, I think that that's typically included within that information. You'd be able to go to that commit in the archived version and see kind of like step before and step after of what those would have looked like. But we haven't looked specifically at that integration.
Before we jump to the next question, I'm just wondering if pull requests would be like a proxy for popularity, which would also presumably correlate with archival rates, right?
Yeah.
So.
Yeah, I think
Maybe.
popular pull requests as well as issues could definitely also be used as engagement metrics. We specifically looked at stars, forks, and subscribers because that was previously done in another study as well. So you're kind of looking at, okay, what would that look like for our corpus, especially in light of kind of the archiving angle.
I think we had a question over here.
Yeah.
Hey, what? Sorry, Jimmy. Did you want to follow up, Jimmy? You can unmute and ask if you want to.
Yeah. So that's kind of where I was getting at, because pull requests would be a good avenue to look into how far this repo was forked, right? People are forking the repo, or fixing bugs, and then submitting the pull request. So that'd be like another way to look at the popularity of the. That's just what I was saying.
Yeah, absolutely. Go ahead.
So I'm just curious, you've kind of identified some pretty big problems or challenges, right? Has there been anyone inside of, the folks who run GitHub? Is there an identification of this challenge in academia, in government, perhaps Library of Congress, other organizations that are looking at this saying, with the rise of software being included in scholarly publications, we're rapidly running into a potential problem, and you recognize there's a problem, there's some potential solutions there.
Yeah. Is
this widely recognized, or is this no one's really paying attention yet?
Okay, so for the folks at home, is this problem being investigated by other people, or what other people are looking into this? So software heritage is like they've identified the importance of software. That's why they're archiving software. That like this is important for the future. But when they're only archiving the software product itself. And so kind of what we're advocating for is that we need more than just the software product. We want to have the entire GitHub experience. Like Jimmy was saying, pull requests matter. Like we talked about, issues matter. It tells us how it got to where it is, not just the code itself. Because there's essentially living documentation that's surrounding this product. So software heritage has definitely identified the problem. In terms of like reproducibility, different like publishers and institutions have identified that reproducibility is a thing, and we should have open access data and software, but they're typically looking at short term. So is is that link that you provided, does it work today? They're not really in, at this point, they haven't really looked into, is that link going to be around for the next 10, 20, 50 years? So, yeah, did that answer your question?
Yes.
Okay.
Yeah, GitHub would never say, gosh, when we die, it's gonna be a problem.
Yeah.
Everyone thinks they're gonna live forever.
Yeah.
Yeah, I mean, including organizations.
Yep.
All those other places, they're gonna die, but we're gonna live forever.
Yes. Yep. Yeah, let's,
Did you look at the difference in the date of the article versus the date of the memento to see if there's a content drift issue with the mementos that are?
yeah, so we didn't include it in this, so that's actually in my thesis. So for more information, go read a whole bunch of pages. Leslie, yeah, yes. Leslie asked about the different, the time delta between, essentially capture versus, the being referenced in a publication, and it was around a year difference between, and that was consistent for both software heritage and the web archives. So there was about a difference. Either it had been archived a year before it was published, so there's probably a lot of work done in between that, or is archived a year afterwards. Again, if it was popular, a lot might have changed. So yeah, that's definitely content drift is definitely something to look at with that, and just in terms of the changes that the code has gone through over time.
I have a question from
Yes.
the slide before,
Oh, whoops.
54, I think.
I was gonna go back to those takeaways. Now I'm not. There we go.
Yeah, so here you mentioned about that 13.3%, that's,
Yeah.
did you check, or I don't know if I missed it, but like how many of those are no longer available on the library? Like, you know, did you go and check
Yeah,
from
so-
13, how many are?
That many. I'm not, I didn't look at, or I'd have to, I think it's in my thesis. Another
Okay.
great
Okay.
takeaway is how many of those
13 like.
Yes,
you know,
are
because that's
actually
on
gone.
web archive, so how
Yeah.
many did we actually get that's
Yeah.
not in library? I was
Yeah.
wondering.
So yeah, of the ones that are gone, only 33% or a third of them are like dead and gone, like they've
Okay.
disappeared completely. So yeah. So that would be categorized like within that percentage.
Okay.
Yeah.
Oh, so of the 13, it's 33. Oh, no.
No. Nah,
There's
yeah.
a different number.
Yeah, there's a different number. It's in my thesis.
Okay.
Chapter 6.
Other questions for Emily? Anything else online, Dr. Wagner?